Hello aspirants. In the previous module, we have seen the fundamentals of spectrophotometric methods. We have also seen the basic principles behind the UV visible spectrophotometry, infrared spectrophotometry, and atomic absorption spectrophotometry. And in the current module, we are going to see UV visible spectrophotometry in detail, the instrumentation part and applications, and so on. We'll see one by one in the upcoming slides. Ultraviolet visible, that is UV visible spectrophotometry, is a technique used to measure light absorbance across the ultraviolet and visible ranges of the electromagnetic spectrum, which we have seen in the previous module, that is the fundamentals, where we covered the principles of spectrophotometry. UV visible spectrophotometry is the spectrophotometry analysis which will be carried out in the ultraviolet wavelength from 200 nanometer to 400 nanometer and the visible region wavelength from 400 nanometer to 800 nanometer. So the UV wavelength range is 200 to 400 nanometer and the visible, that is the color region wavelength, is from 400 nanometer to 800 nanometer. So the colorless solution will be analyzed through the ultraviolet region of 200 to 400 nanometer and the colored solutions will be analyzed through the visible wavelength range of 400 to 800 nanometer. The absorbing species or the drug molecule or whatever the chemical dissolved in the solution will absorb the light maximum in the particular wavelength. So it is a specific property. The absorption maximum at a particular wavelength is a specific property of the drug molecule. So that property is exploited in this particular method. Each and every drug molecule, when you scan with this UV spectrophotometer, it will show you absorption maximum at a particular wavelength like 229 nanometer or 274 nanometer or 310 nanometer, like that, where it will show a absorption maximum. So in that wavelength, the measurement will be taken for the analysis of various samples. According to the Beer-Lambert law, the amount of light absorbed is directly proportional to the concentration of the sample and the distance the light travels through the sample. So there are two factors here. So one is the concentration of the sample. If it is 1 mg per ml and 2 mg per ml and 3 mg per ml, the light more absorbed with 3 mg per ml. That is the directly proportional. The concentration is directly proportional to the light absorbed. More light absorbed with a higher concentration. And also it is directly proportional to the distance the light travels through the samples. So in this instrumentation of UV visible spectrophotometer, the light travels through the sample, the length is same, that is the cuvette length, 1 centimeter or 1 centimeter, whatever the cuvette length, it is going to be remain same. So during the analysis, the only factor which is going to influence the amount of light absorbed is the concentration of the sample which you are going to measure in the particular sample. So the distance the light travels through the sample is also called as the path length, which is constant during the analysis. Hope this is and the entire principles are understood in this particular slide. Now, what is the applications? Why this UV visible spectrophotometry is required? It is used for the identification of the samples through their wavelength maximum. So as I told you in the previous slide, the wavelength maximum is a specific property of a drug molecule or a chemical which will be used to identify the samples. So when you scan the samples, it will show you absorption maximum of 223 nanometer or 274 nanometer, which can be identified with the already reported wavelength maximum of several compounds, so that you can identify the particular compound matching the wavelength maximum which you obtained from the experiment. Then the UV visible spectrophotometer also used for the quantification of the drugs from the drug products using the standards or molar absorptive method. So the assay of the active pharmaceutical ingredient or the finished formulation will be performed using the UV visible spectrophotometer, either standards using the standards method or the molar absorptive method. Then also the dissolution profile will be evaluated for the solid dosage forms like tablets, capsules, pellets, etc. So the amount of drug released at each time point is assayed by using this UV visible spectrophotometry. Then also this particular method is used for the impurity analysis of the solvents, and it can be identified by measuring the transmittance of the solvents. So these are the general application of the UV visible spectrophotometer, and it is widely and commonly available instrument in various laboratories as well as in the academic laboratories. In this particular slide, we are seeing the different parts of UV visible spectrophotometer schematically. It starts with a light source from which a light will be emitted through a entrance slit, and then this light will be dispersed through a dispersive element, and then the dispersed light will be exit through another slit, and then it will be passed through the sample, and finally the light, after passing through the sample, it will be detected through the particular detector, and this entire entrance slit to the exit slit will be comprising the monochromator. In the previous slide, we have seen the schematic diagram of a UV visible spectrophotometer, and in this slide, we are going to see each and every part in detail. The light source of the UV visible spectrophotometer will be commonly used. One is the deuterium lamp, halogen lamp, or xenon lamp kind of light sources. And the wavelength selector, that is the monochromator, will be generally a grating type monochromators to be used for the wavelength selection. In grating with larger groove spacings, filters are commonly used to remove any higher orders of diffraction from the grating. So this is the purpose of these monochromators. Then the light diffracted from the grating is refocused by another mirror onto the exit slit, which is adjusted to accommodate for the dispersive properties of the different wavelengths of the light. So generally these monochromators will be used for the light diffracted from the grating, which will be refocused by another mirror, and then it will be adjusted to accommodate for the dispersive properties of different wavelengths of the light. So it is very important to disperse the light with a different wavelength so that the particular wavelength, the maximum wavelength, can be used for the absorption by the drug molecule. Then it comes to the sample cell. These are called also cuvettes. So these cuvettes or sample cell are either single cell type of instrument or double cell type of instrument. Both are available. So these cells are used for measuring the absorbance or the transmittance. In double cell instrument, the one cell will be used as a reference cell. So generally in the reference cell, we use the blank samples, and the another cell will be used for the sample, which can be changed frequently for different samples. Next important part of the UV visible spectrophotometer is a detector. Detectors are used to measure the absorbed or the transmitted light from the sample, and the light transmitted or absorbed will be converted into a signal by using the detectors. The type and the material of detector will determine the sensitivity and wavelength range of the data that can be acquired. The most commonly used detectors are photomultiplier tube detectors, that is PMT detectors. In addition to that, silicon photodiodes also can be used as a detector, which are sensitive in the ultraviolet and visible wavelength ranges. Then another part is the recorder, which is generally used with the support of a software with a computer system to record the signal transmitted from the detector, from which you can see the absorptions reading, and these readings will be used for the calculations further. In this particular slide, we are seeing a image of typical UV visible spectrophotometer, which is commonly available in a analytical laboratory or a laboratory from the academic institution. The instrument comprises all the parts what we have seen in the previous two slides, like light source, the monochromator, then the detector, etc. We will generally place the samples in this particular portion. If you remove the door, you will find a place to keep the quets or sample cells through which the light source will be passed through. And then you can see the readings in this particular monitor, which is kept above the instrument, and you can note down the reading and do the calculations further. So in this module, so far we have seen some basics of UV visible spectrophotometer and the different parts of the instrument, and also general applications of the UV visible spectrophotometer. And now you wanted to do a analysis using this UV visible spectrophotometer, for which you have to develop a method. And how you will develop a method, or how will you perform the analysis, and how will you find the method availability for the analysis purpose. So you can find generally these methods in the pharmacopoeias. So the pharmacopoeial methods and the molar absorptivity for that compound, which are available in the various pharmacopoeias like Indian pharmacopoeia, British pharmacopoeia, and US pharmacopoeia. And you can directly adopt this method for the analysis which is obtained from the pharmacopoeias. If there is no method available in the pharmacopoeia, you can do a literature search for the method availability, and also we can understand through the literature the physiochemical properties of the various the molecule, like hygroscopicity, water content, solubility, pH and pK values, so that the choice of diluent and other parameters can be decided for the method. So it is important to understand the physiochemical properties of the drug molecule for any kind of analytical method. So that will give you lot of lead for selection of various parameters like diluents and the concentration selections. So different parameters generally used for the analytical method development can be determined by these physiochemical properties. So it is very important to understand these particular properties through the literatures. And then you can develop the new method and validate the particular method for specific method validation parameters. And then you can derive a standard testing procedure for the particular drug molecule or whatever the testing you have planned for. So then you can follow this particular standard testing procedure to perform the analysis at various times. So this is how in general the methods are being developed or adopted for the UV visible spectrophotometer analysis. So how to perform a method development in a UV visible spectrophotometer, we will see briefly in this particular slide. First, the solubility of the molecule, which as I already told, the physiochemical properties are critical for any kind of method. So the solubility of the molecule is very critical for the selection of diluent. The diluent shall be selected based on the solubility of the molecule, and complete solubility is required. Sample preparation procedure to extract or recover the analyte from the drug product is very, very important. Now you are taking a tablet or a capsule or a pellet or some other product. So it is containing the drug as well as the excipients. So now you have to extract the particular drug from the particular tablet or the capsule matrix, which is very important. So you have to develop a method of extraction of drug from the matrix, which is also called as a sample preparation procedure, which we need to develop, which has to give the complete recovery of the particular drug from the particular matrix. For example, in a tablet, if 500 mg of paracetamol is added, then you have to recover all the 500 mg from that particular tablet matrix for the analysis. That entire drug, 100% of the drug has to come out. So this development of sample preparation procedure is very critical for the method. Then to understand the wavelength maximum. So the UV absorbance will be more and provide reproducible results in the maximum absorbance, that is lambda max. So you have to measure your absorption of the samples in the lambda max, that is the wavelength maximum, which should be known for the specific molecule. This wavelength shall be confirmed through scanning the standard, and further standard and the sample absorption shall be measured using this particular lambda max, which we have seen in the previous point as well. Then the interference by the placebo or the excipients or the blank is generally can be avoided or can be nullified using the blank interference or placebo interference. This sample can be kept in the another quet and can be nullified. So in continuation to the previous slide, during method development or during the analysis, the blank interference shall be nil or minimal. Then the UV visible absorbance for any compound shall be from zero point 0.1 to 0.99 or 95, because this is the ideal absorption range for any molecule. If in case if you are getting more absorbance, that is more than 1, then the sample should be diluted appropriately, then the absorption should be taken. As per the Beer-Lambert's law, the concentration of the compound increases, then the absorbance also increases appropriately. Hence, the linearity curve correlation, if you are increasing the concentration, then the absorbance also increases. Then you should get a correlation through a linearity curve, which should be always more than 0.98. As part of method development or a verification or a confirmation of a method, as part of system suitability or the machine is working properly, to confirm that, we always take repeated measurement of standard solution, which will produce the same absorbance. So generally we take minimum of 6 replicates of the samples, which generally give same absorbance. Then we say that the system suitability is passing and the instrument is working fine for the particular method. Then also to confirm the method, we spike the standard in the placebo. Placebo is nothing but the all the components except the drug in the particular given tablet or capsule matrix, whatever the formulation matrix. So except the drug, all the components will be mixed together to form the placebo. In that you are spiking the standard, and it should give the recovery of 98 to 102%. The plus or minus 2% is the acceptable for the recovery, which mimics the accuracy parameter. So this spiking you have to do at 50%. For example, you are going to have the 500 mg of the drug, or you have your 100% concentration is around 10 microgram. Then you have to do 5 microgram spiking, 10 microgram spiking, and 15 microgram spiking. And all the spikings should give a recovery of 98 to 102%. Then the accuracy of your method is perfect. Then the standard and sample solution stability also to be checked. Means the fresh samples give the recovery. Then You keep the samples in for hours or days, and again you check the absorbance and see the same recovery you are getting for the sample on the standards. Then your samples and standards are stable. So the stability of the samples also to be checked. Then finally the robustness of the method also can be checked through by varying the dilute composition, by varying the pH or some other parameters. Yes, minor variation you can give and see that it is not affecting your results of the method, so that your method is very robust. So these are all the certain parameters you need to carry out to verify or confirm your method during the method development or the verification process in the UV visible spectrophotometry analysis. What are the important factors we need to consider during a method development using a UV visible spectrophotometer? So generally the wavelengths or the discrete wavelengths of UV or visible light will be chosen based on the sample property. So the property or the sample property is influenced by the sample composition, which will give you potential information on what is in the sample and what concentration you can expect. So these are the two things which we have to understand before developing a method using the UV visible spectrophotometer. And in case if you are going to use the molar absorptivity method, then we need to understand what is molar absorptivity method or molar extinction coefficient, which is a measure of how well a chemical species absorbed a given wavelength of light. Generally, it is denoted as 1% and 1 centimeter. That means the absorbance of chemical species using 1% of the solution using 1 centimeter path length. So once the method using the UV visible spectrophotometer is developed, then finally you have to use certain formulas to calculate the standard absorbance or the sample absorbance or the molar absorbability. In case if you are going molar absorbability method, then you have to calculate the sample concentration using molar absorbability method or sample concentration using a standard absorbance. So in molar absorbability method, where 1% and 1 centimeter is the specification, the sample concentration is equal to sample absorption into sample volume into 1000 divided by molar absorptivity into sample weight. This molar absorptivity you can get it from the pharmacopoeias of particular reference. Then the sample concentration using standard absorptions can be calculated by using this formula. Sample concentration mg by gram is equal to sample absorption standard weight into sample volume into 1000 divided by sample absorbance into standard volume into sample weight in grams. You can also determine the sample concentration using linearity methods. So linearity method is constructing the calibration curve by using various linearity standards, right from the lowest concentration standard to the highest concentration standard, which will give you absorbance directly proportional to the concentration, increasing trend of absorption, which will give you a calibration curve through which you can construct the equation of y is equal to mx plus c, where the slope and intercept is nothing but m and c, and x is the concentration of the sample, y is equal to y is nothing but the absorbance of the sample. So to calculate the sample concentration, you have to deduct the intercept from the sample absorption, and that is y minus c divided by the slope of the linearity curve, that is the m. So y minus c divided by m will give you the sample concentration. Then finally, you can calculate the purity by using the obtained sample concentration, that is x into the sample dilution divided by the sample weight used for the standard preparation. So in this particular slide, we are going to see certain examples of pharmaceutical applications of UV visible spectrophotometry. So generally, as we already seen that the active ingredients, pharmaceutical active ingredients or active pharmaceutical ingredient API or the API in the drug product will be analyzed or the impurities will be analyzed using the UV visible spectrophotometer. For example, estimation of ciprofloxacin in each tablet or eye drops in any formulation can be performed by using UV visible spectrophotometer at a wavelength of 276 nanometer. Also, metformin can be analyzed using UV visible spectrophotometer analysis using the wavelength of 232 nanometer. The matrix can be tablet or capsule or a solution formulation. The colored solutions also can be estimated in the visible range of 400 to 800 nanometer. For example, cyanocobalamin can be analyzed using wavelength of 278 or 361 or 350, 550 nanometer. In a analytical laboratory setup in a pharmaceutical industry or any other industry, the calibration of the instrument is important step to ensure that you are getting right results. The calibration involved various parameters for a specific instrument. For UV visible spectrophotometry, the parameters like control of absorbance, control of wavelength, resolution, limit of stray light are the four different parameters need to be calibrated at time to time for the instrument. What is control of absorbance? It is useful to measure accuracy of the absorbance using the primary standard potassium dichromate solution. So when you calibrate your instrument, you have to use the standard potassium dichromate solution to measure the absorbance to see the accuracy of the absorbance. Then control of wavelength. It is useful to measure the wavelength accuracy by using the primary standard of holmium oxide solution. Similarly, you have to measure the wavelength accuracy by using this holmium oxide solution for the calibration of your instrument. Then the resolution will be checked. It is useful to measure the resolution between the wavelength maxima and the minima. And the limit of stray light will be used or useful to measure the stray light is not affecting the absorbance measurement. So these are the four critical parameters will be carried out during the calibration of the instrument to ensure that you are getting appropriate or real results consistently using this particular instrument. In this slide, we are going to see how a control of absorbance will be carried out during a calibration of your UV visible spectrophotometry. The control of absorbance will be carried out by using potassium dichromate solution 0.06% in 0.0005 m molar sulfuric acid, and this solution will be scanned through UV range of 200 to 400 nanometer. So when you scan this particular range and when 235 nanometer wavelength, you should get the absorbance of 124.5, and the limit will for this particular wavelength is 122.9 to 126.2. So if you are getting these results within this limit, then the control of absorbance is good for your instrument. Similarly, for other wavelengths, the acceptance criteria is given based on which the instrument is calibrated for the control of absorbance. In addition to the control of absorbance, the control of wavelength will be verified using absorbance maximum of chromium perchlorate solution at different wavelengths. The acceptance criteria is the permitted tolerance of plus or minus 1 nanometer in the range of 200 to 400 nanometer and plus or minus 3 nanometer for the range of 400 to 600 nanometer. Then the resolution will be verified by recording the spectrum of 0.02% volume by volume solution of toluene in hexane in the range of 260 to 420 nanometer. The acceptance criteria is that the ratio of the absorbance at the maximum at about 269 nanometer to that of the minimum at the 260 nanometer is not less than 1.5. During calibration, the limit of stray light will be examined or verified using a solution of 1.2% weight by volume potassium chloride in water. The absorbance of this particular solution will be measured at a different nanometer wavelength using water as the blank. The acceptance criteria is that the absorbance of this particular solution, potassium chloride solution, in a 1 centimeter cell should not be greater than 2 at about 198 or 200 nanometer. So aspirants, in this module, so far we have seen the basic principles involved in the UV visible spectrophotometer, and then the different parts of UV visible spectrophotometer, the instrumentation involved in the UV visible spectrophotometer, and the general considerations of method development using a UV visible spectrophotometer, and the calculations involved in the measurement of concentration using the UV visible spectrophotometer, and then the general procedures adopted for calibration of UV visible spectrophotometer. And in detail, we will see the method development and validations of these analytical methods in different modules in the upcoming modules. And in the next module, we are going to see another spectrophotometric method, the infrared spectrophotometric meter. Wish you good luck. Thank you.